Now that we've done the particle in the box and we've learned a little bit about quantum interference and whatnot, it's time to start thinking about how quantum operators actually work. So basically this is about munching on functions. Remember that operators are objects that have a little hat, of course, and they chew on a function. And the key characteristic is that when an operator chews on a function and it poops out a constant times that function, it's a special thing. So this little video is going to be about how operators work. And the key is that that function phi is an eigenfunction of the operator, and that value lambda is called the eigenvalue of the operator. And not all functions are eigenfunctions of a given operator, and that turns out to be a critical aspect of quantum mechanics. For our first example, let's consider a problem that we've already solved. The kinetic energy operator, T with a little hat, is equal to minus h bar squared over 2m times the second derivative with respect to x, d squared over dx squared. And we call that the kinetic energy operator. The fact that we call it a kinetic energy operator is important. Now the question is, phi equals sine of n pi x an eigenfunction of that kinetic energy operator? Well, let's see. If we operate on phi with t, then we get the second derivative. So we've got inside n pi, we're going to poop n pi out twice. So we're going to get n squared pi squared and a minus sign. And then the operator itself has a minus sign, so that goes away, and we've got an h bar squared over 2m. So that all gives h bar squared pi squared over 2m n squared times sine n pi x. Second derivative of sine x is minus sine x. So let's see, that looks pretty good. Yep, we have some quantity times sine n pi x after we've munched on our function phi with the operator t. So sine of n pi x is said to be an eigenfunction, and the quantity h bar squared pi squared over 2m n squared, that is the eigenvalue of the function. Alright, well, let's try another thing. How about, let's say phi is equal to x squared. Is x squared an eigenfunction of the kinetic energy operator t? Well, t operating on phi is just going to take that second derivative, which is just going to produce a 2, and then remember there's a minus h bar squared over 2m, so 2 kills the other 2 in the denominator, and we get minus h bar squared over m after t finishes chewing on phi. And what it spits out is not some number, lambda, times x squared. There's no x squared in there. So it's not just a constant times x squared. We killed the x squared. So x squared is not an eigenfunction of the kinetic energy operator. So what? Now it's going to get a little bit strange as we start to work our way into the quantum mechanical world of eigenfunctions and eigenvalues. So let's keep thinking here. So an operator in quantum mechanics is basically how we measure stuff. It's a representation of how you make a measurement of something. So in other words, t hat is basically how you ask a function phi, what's your kinetic energy? And the deal is that in this case, the answer is the eigenvalue. So if I've got a function phi, and it is an eigenfunction of some operator, and I ask it, yo, what's your energy, or what's whatever, then it's going to spit out the eigenvalue lambda, and that's going to turn out to be the answer to that question. So in this case, h bar squared pi squared over 2m n squared is the kinetic energy of the function phi, which is sine of n pi x. And the way we ask it that question is to chew on it with, we let the t operator out of the pen, and it chews on the poor function and kind of gives up the answer. And that's what we're going to spend most of the class doing. So basically, operators and the eigenvalues associated with those operators are what I call the secret decoder ring of quantum mechanics. They are basically just how we ask questions of quantum objects, of little tiny wave-particle duality thingies that are represented by a wave function. What that means is that every observable that we might think to find out, everything there is to know about an object, because remember that wave is the object, every observable has to have some sort of operator associated with it. And part of the trick is to figure out what those operators are and how they work. We started with one operator, and that's the kinetic energy operator. So again, t hat kinetic energy operator is minus h bar squared over 2m times the second derivative. It's getting kind of boring just doing kinetic energy, so how about momentum? Momentum's a nice quantity from physics. It tells us something about both how fast something's going, but also its direction. So what about momentum? Well, remember that in classical physics, the kinetic energy is given by the momentum squared divided by twice the mass. Energy is p squared over 2m. So I can rearrange that to get the momentum is plus or minus twice the mass times the kinetic energy, all under a square root sign. And the plus or minus is because of the square root. We can take a positive or negative number, and as you'll see, that's going to be useful in a second. So let's start to do something a little weird. Let's take the negative sign of that plus or minus square root there, and work away on the kinetic energy in quantum mechanical terms. So I'm going to take minus square root of twice mass times that kinetic energy operator. So that's minus square root of, let's see, there's a minus 1 h bar squared, and then a second derivative, and so that's equal to minus the square root of minus 1 times h bar, and then the square root of the second derivative there. Okay, well, the minus square root of minus 1 bit, that is minus I. Remember, the square root of minus 1 is I, the imaginary number I. And I've got an h bar, and I still have this square root of the second derivative. Well, why don't I just kind of pretend here that the square root of the second derivative is the first derivative, right? The square is there. Why can't I take the second derivative? So we got minus I h bar d by dx, first derivative. Now hang on, if you know anything about math, you know I can't actually do that. I can't take the square root of a second derivative and get a first derivative. But it turns out that that's not just a bad thing to do. Even though it's not mathematically valid, it is a little trick that allows us to manipulate operators and figure out what the right operator is. So as a ploy to figure out the operator, it does work. So the momentum operator, p hat, there's the hat again, is in fact minus I h bar d by dx. So the first derivative times h bar, and with a minus I out in front, is the operator that expresses, that tells us momentum, that will chew on a function and give us the momentum back. Alright, so let's try out our momentum operator on the particle in the box. So what's the momentum of a particle in a box? Well, let's see, we got psi, that's equal to the square root of 2 over L times sine of n pi x over L. And we can operate away on that, chew on that with our momentum operator. P hat times psi is equal to minus I h bar times the first derivative of the square root of 2 over L sine n pi over Lx. That is equal to, let's see, we got a minus I h bar, and we get a pi and an n divided by L pooping out of the sine, times the square root of 2 over L times now cosine of n pi over Lx, because the first derivative of sine turns it over into cosine. One thing you'll notice is that I'm keeping that normalization term, square root 2 over L, tied really, really closely to the function sine or cosine. And that's going to be, you should do that whenever you're doing this, because you don't want to let that normalization term float out there and confuse it with the eigenvalue, okay? But in any event, cosine is not a multiple of sine. So what that means is that psi is not an eigenfunction of the momentum operator. The particle in the box wave function, square root 2 over L sine n pi x over L, is not an eigenfunction of the momentum. So we tried to find the momentum and we didn't get a sensible answer in some way. What does this mean? Does it mean that the particle in the box doesn't have any momentum? Nah. That would be kind of stupid. It doesn't mean that. It means something else, but exactly what it means is something we got to work on a little bit. But it can't have no momentum. There's energy. There must be some sort of momentum associated with that. But we don't get a good answer by just trying to chew on our particle in the box wave function with the momentum operator. So we got to think about this a little bit harder now. Well, to start to work on this, let's consider a totally different function, because sine kind of let us down here. So how about a function, let's call it phi, and it's going to be e to the I n pi over Lx, or exp of I times n pi over Lx. So I find it a little easier to write the exp function notation than e to the power of, because it gets that little exponent up there. In my terrible handwriting, it's really, really hard to read. So exp of x is equal to e to the x, okay? Standard programming way of representing it. So let's pull this function out of the hat here. Now that's a complex number. That's what we call a complex wave function, and we're going to do a lot of that in the course of this term. In fact, it's going to be a major player, but right now we don't have to worry about it too much. Let's just consider a couple of things about this. So don't panic, but the first thing I want to do with this function is let's think about normalizing it. And we're still kind of playing with a particle in a box situation where we have a box between 0 and L, and so that means that my normalization, if I were to normalize this wave function, I should get 1 if I integrate from 0 to L the magnitude of the wave function squared, right? That's the meaning of normalization. And right now is when why I put this silly magnitude around the wave function is going to become apparent. Because that's equal to the integral from 0 to 1 by dx of the complex conjugate phi star times phi. That's what magnitude squared means. And phi star is the complex conjugate of a complex number. And actually for e to the I nx, e to the I kx, it's really easy to deal with. The complex conjugate of e to the I x is just equal to e to the minus ix. You just change the sign there in the term, in the exponent of e to the x. And that's actually a pretty good thing, because that means, 1 is equal to the integral from 0 to L of e to the in pi over Lx times e to the minus in pi over L x dx. So I got e to the I n pi over L and e to the minus I n pi over L. It's the same thing in the circles there, right? So it's just the same number plus and minus by dx. Well, e to the x times e to the minus x is equal to 1. So this thing is just the integral from 0 to L of dx. And that's just equal to L. So the thing is really easy to integrate. The thing about those complex conjugates is that, especially when I have this e to the ix form, you multiply the function by its complex conjugate, and it has this really nice habit of just turning into 1. So even though I have this complex wave function, and we're going to eventually worry about what that means in different situations, right now it turns out that at least for the purposes of normalization, it's really, really easy to deal with. Alright then. So now I have psi of x is equal to the square root of 1 over L times e to the I n pi over Lx. That's a fully normalized wave function, Notice it's square root of 1 over L now. E gets a slightly different normalization, but it should look pretty familiar. So let's see, for starters, since we've been doing kinetic energy a lot, is this thing an eigenfunction of kinetic energy? Well, first derivative of this is equal to, we're going to poop out an I n pi over L, and then we still have our square root 1 over L, and then we have our e to the I n pi over Lx, because the derivative of e to the fx is just equal to f e to the fx. You take derivatives of e to the something and it just kind of blasts out whatever is multiplying the dependent variable there. So let's do it again. Second derivative, and now I'm going to get a minus sign times pi squared over L squared n squared times the square root of 1 over L, and then an e to the I n pi over Lx. That minus sign came out because another I came flying out, and I times I is minus 1. So that's where that minus sign came from, and then the pi squared n squared over L squared is because I keep flinging out the rest of the multiplier on x, and then the root 1 over L is the normalization term, which continues to stay very tightly, clings tightly to the function there, e to the I n pi x over L. Okay, so now we can take that and actually find the kinetic energy operator T psi. That's equal to h bar squared pi squared. That's just a 2m that pops in over 2ml squared times n squared times the square root of 1 over L, e to the I n pi over L times x. So I just had the 2m, the 1 over 2m came in. There was a minus sign in the t operator, and that canceled out that minus sign in the second derivative, and so that's what we get there. And looky, I've got now square root 1 over L e to the I n pi over Lx. So that's equal to h bar squared pi squared over 2ml squared times n squared times psi. I've got the function back. So yes, this thing is an eigenfunction of the kinetic energy operator. Not only is it an eigenfunction of the kinetic energy operator, the kinetic energy is equal to h bar squared pi squared over 2ml squared times n squared. Now that is one really familiar looking thing. Those are the energy levels of the particle in a box, as long as n is equal to 1, 2, 3, 4, 5, etc., all the way up onto infinity. So I get the exact same energy levels out of this function. Well, alrighty then. How about momentum? Is psi equal to square root of 1 over L e to the I n pi over Lx an eigenfunction of momentum, of the p hat operator? Well, p hat's equal to minus I h bar d by dx. We already did the d by dx, so p psi is equal to h bar pi over L times n times the square root of 1 over L e to the I n pi over Lx. We just got that I n pi over L pooping on out, and we picked up an h bar, and we had a minus sign sitting there, and the I coming on out canceled out the I in front of the momentum operator, and there was a minus 1 sign sitting out there, and then that's actually why we have the minus sign on the operator, and so we just wound up with a positive h bar pi over L times n, multiplying something that looks suspiciously like our wave function. So yes, indeed, p operating on the wave function is equal to h bar pi over L n times the wave function. So it is an operator, it is an eigenfunction of the momentum operator. Remember, Dirac-Pourol's sign wasn't. This one is. And the momentum itself, the eigenvalue, is equal to h bar times pi divided by L times the quantum number n. That h bar is going to hang out a lot, and that's going to be important. And there's one other thing that will eventually crop up here. It's a really interesting bit, because you associate momentum with mass in classical physics. But in quantum mechanics, there's no mass. The mass has nothing to do with the momentum. And remember that from the de Broglie relation, the momentum is going to be related to the wavelength of a wave function. The actual mass showed up in the energy, but there's no mass expressed in the wave function quantum mechanically. It's just the wavelength of the wave function. And in fact, that's why photons can have momentum, why protons and electrons can have momentum, because they all have wavelength, and that's what momentum is associated with. So there are a lot of differences between quantum mechanics and classical physics, and this is one of the really early profound ones, and it's actually really pretty important. So this particular wave function we've chosen is an eigenfunction of both the momentum operator and the kinetic energy operator. Sine wasn't, this one is. And that's kind of special. The other thing you should notice is that square root of 1 over L term, that normalization term, didn't bother us at all. Remember, we said that earlier on when we were talking about normalization in the first part. We do need to make sure that when we integrate up the magnitude squared of the wave function over the appropriate interval, we get 1 to ensure the probability distribution is right, that the probability of finding the particle inside the box in this case is equal to 1. But often, because we're dealing with multipliers, that term multiplying the function in the normalization just kind of carries along, and as long as you make sure it grabs onto the function tightly and sticks right next to it, you're always going to be able to cancel it out without any real trouble. So since this thing is an eigenfunction of the kinetic energy operator and the momentum operator, and it's got the same energy levels as our first original particle in the box solution, why didn't we use it in the first place? It's great. It gives us kinetic energy, it gives us momentum, it's a complex number, but so what? You have to deal with some things. So it seems great. Here's the problem. E to the in pi over L times 0, if x equals 0, is equal to e to the 0, and that's equal to 1. That's not so good. Remember, the boundary condition of the particle in the box, because the wave function had to be continuous, was that the value of the wave function at x equals 0 had to be 0. So the complex e to the in pi over Lx does not match the boundary condition, because it had to be 0 at 0. In fact, it has to be 0 at L as well. So for that reason, this simple e to the in pi over Lx, even though it's an eigenfunction of both momentum and kinetic energy, doesn't match the boundary conditions, and it doesn't work. Sine does, and so sine wins out.